Our task today is showing that the theta operator, which we defined when we were converting the Helmholtz equation to its factorial form and with epsilon varying as a function of r. So our task is to show that this theta operator is a Hermitian operator. So let's roll up our sleeves and get started. And let's get started with some auxiliary lemma, which is based on the following vector identity. If you have the divergence of a cross product, a B, then this can actually be written, it turns out, as the following, as B inner product and then the curl of A, and then minus A, and then the inner product, and then we have the curl operating on B. So this will be a useful starting point for our lemma. What I suggest you do is pause the video and take the volume integral of this equation here and see if you can simplify things based on the divergence theorem. So taking the volume integral is pretty straightforward. So we have the volume integral of the divergence of a b dv, and then this thing is equal to a volume integral of b, and then we have curl a dv minus volume integral, okay, so there we go, curl of b dv. Extremely trivial. What we're going to do, how we're going to write this, is we're going to bring this guy here to the left-hand side. And then we can write that the volume integral of A, then we have divergence B dV, that we can write this as, and then we take this term over here, but we exchange the order here. Then we have curl A B dV, and then we have minus a volume integral of the divergence, which is going to be a surface integral of the stuff that's being taken the divergence of, like this. So this is going to be simplified, sorry, as a surface integral. Okay. Now, why on earth are we bothering with doing all these manipulations? What's the goal here? Well, remember, our ultimate aim is to try and show that the theta operator is Hermitian, namely that it doesn't really matter if you first operate on the second factor or first operate on the first factor before taking the scalar product. So what we should do in our proof is somehow start from the theta operator, for example, operating on the second factor, and then try to reassemble that theta operator such that it operates on the first factor. Now, our theta operator contains lots of curls. And what this equation actually shows us is how we can take a curl, which is operating here on the second factor, and move that curl to the first factor. So basically we can do that, but there's a price to pay, and the price here is exactly the value of this, this surface integral. So this is why this is such a useful lemma for our purposes. Okay, so now we can get started with the work proper. So we have the following starting points like this, and then we need to show that we can have that theta operator first operating on F as well. So this is our ultimate goal. So pause the video, start from this guy over here, introduce the definition of the theta operator, and then see if you can use this lemma to unpeel, for example, the outer layer of the onion that is the theta operator and bring it to the first factor so that it operates on F. Okay, so what do we have? If we have the definition here, our scalar product is a volume integral of the complex conjugate of the first vector function. And then we have the second vector function, which is the theta operator operating on G. So the theta operator, remember, is curl 1 over epsilon curl. Okay, so this is what that scalar product actually looks like. Now, if we want to use our lemma here, what is the A and what is the B? Well, obviously this is going to be taking the role of A, and then this whole thing here is going to take the role of B in our lemma over here. So that lemma tells us that we can basically take the curl which operates on B and move that so that it operates on A. So we have our volume integral of the curl of complex conjugate of F, and then here in the second factor we have 1 over epsilon and then our second curl dv. And then there's a price we pay in terms of that surface integral, but what we're going to do in our particular case is we're going to say, well, that contribution will always be 0, so we're not going to bother with that. Why can we say that that contribution is 0? Well, typically we look at the whole volume of the entire space, so this surface integral is a surface integral at infinity. And then you could either say, well, typically at infinity, the fields will be 0 because they decay there. So that's one possible situation that you can have. Or you could also be in a situation where you're dealing with periodic media, which will result in periodic fields, which are positive and negative in a periodic fashion. And if you integrate them out over the entire surface at infinity, then all the positive contributions will cancel all the negative contributions. So let's restrict ourselves now to situations where either one of these things is true, such that we don't need to pay the price of that surface integral. Okay, so then this starts looking a little bit like what we need in order to have our theta operator operating on our first factor. The only thing which we would really like to have here, but which can be trivially accomplished, is we would like to write the following, where the complex conjugate operates on the entire curl of F and not just on F. But that's of course something we're allowed to do because this nabla operator is just partial derivatives. So if we take complex conjugate, that doesn't come into play. It's a real valued vector if you want, symbolic vector. So therefore this means we can write this as follows. Right. So if we take a look at our theta operator, it had 3 layers in its onion. We had a curl, we had 1 over epsilon as the second layer, and then another curl as the inner layer of the onion. So we've peeled away the outer layer and reassembled it over there. Now the outer layer here becomes the inner layer there. Let's look at the middle layer. Then we have this 1 over epsilon here. Question is, can you bring this 1 over epsilon to the first factor, namely inside the complex conjugates? And if so, under which circumstances are you allowed to do that? So think about that for a while. So ideally, you would like to write this as the volume integral of 1 over epsilon curl F complex conjugates, like so. So the only way you can take this epsilon inside the complex conjugates and still leave everything intact is actually when epsilon is actually a real number, so that the complex conjugate doesn't matter. Real epsilon, that means we have lossless media. Okay, either lossless dielectrics or lossless metals, but as soon as you have a real epsilon, then you're allowed to do that. Right. And then pause one more time and try to peel away the final layer of the onion and then show that this theta operator is indeed Hermitian. So if we now apply our lemma again, but this time this here plays the role of A, and this plays the role of B, and we just apply the lemma one more time. Again, making use of the fact that the nabla operator is a real valued vector. So then we get the following curl of F complex conjugate, and here we have our lonely second vector function, dv. And again, there's a price for the surface integral, but we've decided not to pay that price because we're working in situations where the value is 0. Then basically what we have here is the definition of the theta operator first operating on F and not on the second factor. So we have indeed shown that these two guys are the same, so it doesn't really matter whether you have your theta over here or over there. So our theta operator is indeed Hermitian, provided you're working in lossless media and provided you're working in a situation where this price of the volume integral over the surface integral over there is actually 0.